Okay, fighting through my technical difficulties. Everything I had working until class today. The recording didn't work for my last class because there's a new version and it turned off the recording, I found out just now. And PowerPoint, I had it writing the right place. I got it going actually right after class ended on Monday. And then just before class today, it started writing the wrong place again. So we're doing PDFs instead of the PowerPoint, which will be fine since the clicker is not working to advance the PowerPoint at this point. So who cares, right? Only me. Did you all get the reading quiz done? They never sent me a thing saying it's up and running. I also noticed this morning when I sent the message that there was a banner message saying that it may not work, but everyone but DJ had at that point, well, everyone who had logged in at that point had done it. So I assume it worked for everyone. I apologize for the difficulties there. It's outside of my control, thankfully. Okay, we've been talking about electric charge. One of the interesting things about electric charge is that it's intrinsic. There is no source we know of for electric charge. It's just something that some things have. And how do we know about electric charge at all? Because we can measure the force, the interactions that result from electric charge. So electric charge is really inferred. Because we see these forces, we infer the electric charge. And if you take the time to wander off into particle physics, you find that things like the up quark, the down quark, they're inferred. Nobody has ever found an up quark per se, but we are measuring different properties and inferring that there must be this object that we call the up quark that contains certain intrinsic properties such as the charge. And I talked about the charge of the up quark is 2/3 of the fundamental charge. And it sounds wrong. Fundamental means it's indivisible. It's the basic. How do you have something that's 2/3 of the fundamental charge? Well, we never find quarks in isolation. We only find them in combination, and those combinations always give us integer multiples of the fundamental charge. What is the fundamental charge then? Charge of an electron. So E is equal to 1.602 times 10 to the minus 19 coulombs. That's the fundamental charge. An electron has a negative 1.602 times 10 to the minus 19 coulombs. A proton has a positive 1.602 times 10 to the minus 19 coulombs. Neutron has 0, but we obviously don't consider 0 the fundamental charge. We've also learned about these charges, that there's a force associated with them. And as I just said, we actually learned about the charges by looking at the force, not the other way around. So if I have two charges, we have rules. Two rules about the force. Rule number 1 is that opposites attract and likes repel. So as the picture up there shows, two positive charges are going to be pushed away from each other. A positive and a negative, shows a positive and a negative are attracted, and two negatives are pushed away. The second one is that the force is always parallel to the direction between the two. So you can't have a positive and a negative like this, and then a force that makes it go that way. It's always going to have to be the force is parallel to the line connecting the two. And then we had Coulombs Law to give us how big the force is. Coulombs Law, change colors to something that will contrast with that, is the force due to electric charge. I'll put a C here for Coulomb today. Has a magnitude that's equal to a constant K times one charge magnitude times the other charge magnitude over the separation between the centers of the charge squared. That's Coulomb's law. I wrote it here as a scalar. That is without a direction to it. There is a direction to the forces, but use the first two things I talked about, opposites attract, likes repel, and that the force is always parallel to the separation to determine the direction of the force. So anytime you're using this law, I recommend throwing on absolute value sign here. Just calculate the magnitude of the force and then use your geometry to determine the direction of the force. Now, lab yesterday, I believe we had a lot of fun. Oh, yeah, I have this question. Please tell me, what's the answer? What's the fundamental charge? Okay, I hear multiple answers now. B. That's the fundamental charge. What is this here? It's 1 Coulomb. That's giving us our basic unit of the Coulomb, but it's not the fundamental charge. Oftentimes people will try to say, oh, well, the unit must be the fundamental. No. The fundamental means the smallest piece you can have. And we don't count 0 as the smallest piece. That's just without charge. So everything is an integer multiple of 1.602 times 10 to the minus 19 coulombs. Everything. Just for grins, what is this number? It's Avogadro's number with a C written after it. Yeah. Okay. We had a group that illustrated charging by conduction and induction, and they did a nice job. So I'm not doing this because they didn't do a nice job, but because it's always worthwhile to have a review on the process. So conduction is a direct transfer. So I'm going to use this as a prop today, not to charge anything up or to get shot. So let's say that I have this. Here's a metal rod. And this metal rod has, I'll be realistic. I have a glass rod, and I rub the glass rod on my shirt, which is polyester, but we'll pretend it's silk. So if I rub this on my shirt, electrons, now we have some better understanding, electrons move from the rod to my shirt. So this is short of electrons. Now remember, the protons are fixed in the atoms, and the atoms don't move. The electrons are bound to the atoms, but we could take electrons off or add electrons to it. So here I took some electrons off. It's short of electrons. So the number of protons is the same, number of electrons is dropped, so it has a net positive charge. I bring it close to here. I'm not touching it yet. I bring it close to here. Since this is positive, what's it going to do to the electrons that can move on the conductor? It's going to pull them. So as I bring it close, I'm going to have a bunch of electrons come over here, leaving behind protons without an electron over here. So this side becomes positive because it has missing electrons. This one's negative because the electrons move from here to here. Now if I touch it, then I'm going to have electrons go from here to here, and that's the conduction. So now electrons have left this. I take it away. This is missing electrons, so its charge is now, if it's missing electrons, what is its charge going to be? Positive. Now that's conduction. If I did the same thing, I don't know why I'm charging this rod up when I'm not actually doing anything. So this is positive again. And let's say I touch this, so electrons are just free to move onto my body or off of my body. It's neutral. I bring this up here, just like before, electrons are attracted over here. If I touch here, what's going to happen? This is pulling electrons. I touch here, what's going to happen? Well, protons can't move. Okay, it's going to pull out electrons from me onto this because this is attracting them. And so I would have electrons move onto this from my body. I have to take my hand away first. If I leave my hand on here and take this away, the electrons just go back to my body. But if I go like this, touch it, electrons leave my body, take my hand away, now they're trapped. Take this away and it's got a negative charge, the opposite charge. Now I was talking about touching here. What if I brought this up here and I touched it here? What would happen then?
The electrons will just stop in your body?
It actually makes no difference. It's still going to do the same thing. Electrons will come off my body because this area here was positive. It wants electrons. I put my finger here. It's going to pull the electrons from my body, come back here, and make that neutral. And so it's still going to pull electrons off my body no matter where I touch it. So the effect is the same. It doesn't matter where you touch it. It matters that you touch this, you bring this close, you disconnect this before you take that away. So induction, you induced a change. Conduction, you actually conducted them away. So I've got pictures for both just to make it clear. And you can see here, If you zoom in, it's not touching. Close, but not touching. One thing I didn't talk about in regards to this, when I did this action here, so here I'm going to actually do something. Charge this up, bring it up here. I can have some arcing that goes through the air. Now we had the group with Ryan, Chad, and Madison, they looked this up. If I have a voltage difference of 3 kilovolts per millimeter, I can actually have electricity pass through the air. So depending on now we haven't even talked about what a kilovolt is yet, but depending on how much charge I have on here, I can have arcing occur without it actually touching. The arcing would be a conduction. So the inductive charging is presupposing that you don't have the arcing also occurring. I'm touching this, it's charged up. If I rub it around, I can charge it up more. Why can I charge this up more if I rub it around instead of just touching one place?
The electrons don't flow in insulator.
This is an insulator. I have I have missing electrons. And different places have different missing electrons. When I touch it, electrons will flow from that conductor to replace missing electrons. If I move it, I'll get to a place that has more missing electrons, I'll have more flow in. Because this is an insulator, I actually am going to do better by moving it around and rubbing it. Whereas if it was a conductor, I would just touch it. It wouldn't make any difference if I moved it around. So understanding some of the differences between conductors and insulators is important. I think Nathan was the one who explained what causes conduction versus insulation. You have in the metal, most of the electrons are bound to atoms. But every atom is giving up 1, maybe 2 electrons, maybe 3, that it's not holding tight. The valence electrons are not held tight in this. And so those electrons that aren't held tight, it's kind of like water. The water molecules are held together. It would take energy to pull them away from the water, but they're free to move within the water. The electrons are doing the same thing here. In fact, we talk about it as an electron fluid. We have a fluid of electrons in here. And so since they can move around with virtually no energy, if I put some charge here, everything will redistribute because it can do that. With an insulator, each atom is holding on tightly to all of its electrons. So none of the electrons are free to move. Hence, with the insulator, you can't have charge move across it. So that's our difference between an insulator and a conductor. A very practical example in illustrating that not all materials are as simple as what I've just described. This is the basis of how a photocopier works. Now, photocopiers, obviously, you have a lot of care in the design, but here's the basic thing. You start by taking a piece of paper and putting a bunch of positive charge on it. Now, I say put a bunch of positive charge on it. I'm very comfortable saying that. But what's really happening? I'm taking electrons away from it. We always have to keep in mind the physical reality compared to the words we use. So that charging plate is taking a bunch of electrons away from the paper. So you have negatively charged paper. You have that negatively charged toner brush. You guys know what toner is? If you've ever had to work with a photocopier, you know that toner is a powder that gets everywhere, right? That is what we consider ink. The toner is the, quote, ink. So you have that powder, and that powder is put on a wheel and given a negative charge. So right away you can say, positive and negative. What happens if we bring the powder, the toner, in contact with the paper?
It's going to aggregate where the charge is.
Yeah, the positive charge on the paper and the negative charge of the toner is going to make them attract. But how do we get a pretty picture from that and not just make a full page of black? So that's where this selenium-coated drum comes in, the center part. The selenium is has a really interesting property that it's an insulator, but if you shine light on it, it becomes a conductor. So it's a photoconductor. Light makes it conduct. And so you have another charger that is, quote, putting positive charge on, in reality, taking electrons away from that selenium. So you have positively charged selenium. That was interesting. I don't know how that was chosen, but it is an option. There we go. You have positive charged selenium there. Now, selenium is a solid. It's just moving along. And then you have a light mirror system. Now, this is, let's say, a primitive system. I'm sure the systems today are not quite so primitive. But it's just shining a bright light on your paper. And then that bright light from the paper is focused onto the selenium drum. And if the paper was black, then you have no light being put on the drum, and it stays insulated, hence it stays positive. But if you have light shining, so if you have white paper, then it shines the bright light on the selenium, making it conductive, and the positive charge then goes through to the center of the drum. So it has essentially a ground. It shows plus at the center, but it basically has a ground underneath that selenium coat. So the positive charge, well, electrons come up from the ground to neutralize anywhere the light shines. So in the end, on the top of the drum here, we have a reproduction of whatever was on our paper in positive charge. So now we have the drum and the paper come together. The drum and the toner come together. The negative toner attaches to the positive parts of the drum. So the drum will have toner on the positively charged part, nothing on the rest. Then we press down the paper. The paper is more positive than the drum. Hence, the toner shifts from the less positive drum to the more positive paper. And so now we have toner in the paper to make our picture. If you've had a problem with the photocopier before, you pulled out paper like that was jammed in there, you found that the toner will come off the paper. So the last step is that heater. That heater melts the toner. The toner is like plastic. Little plastic dust, you melt it into the paper, and then it's going to be fixed in the paper and won't come out. So a photocopier, when you think about all of these pieces, each piece itself is simple. Each piece is definitely something you can understand. But to put all those ideas together takes a pretty good mind, right? It's not obvious that, oh yeah, I can reproduce something by using this photoconducting selenium, and I am impressed by people who come up with things like this. And by the way, this heater thing is why you can't just put overhead slides through a photocopier. You have to have special high heat slides to be able to make a photocopy, and otherwise you melt them. And that's a mess. Just in case, overheads aren't used that much anymore because we have things like this. Do you have a question? Or is, no? I saw your hand go like this, but now I see that you had your drink that you were touching. Coulombs Law, of course, we introduced it last class period. I wrote it on the first slide here. We've talked about it. Last class period, once again, it was Nathan who asked about the point charge. Or was it, maybe it was Tuesday when he asked about the point charge. A point charge means a charge at a single point with no volume. It's not a realistic thing, but it's a physics thing. It's something we use to understand and think about. Everything in life is not exactly a point charge, but oftentimes we can approximate it as a point charge. The force, when I'll write the force law again. It's an inverse square law, meaning that the force is inversely proportional to how far away things are. That's an important implication. If we make charges farther apart, the force drops off dramatically. If you double the distance, what's going to happen to the force? Going to decrease by what factor?
4.
By 4, because 2 squared is 4. If we triple the distance, it'll drop to 1/9 the force. So that inverse square law is important, and of course, the force of gravity was also inverse square law. So basically, everything we've learned about gravity really applies to the electric force as well. The difference is gravity was unipolar. All of the gravitational charge, otherwise known as mass, was positive. Electric force is dipolar. You have both positive charges and negative electric charges. And so you have the option of repulsive as well as attractive. Gravitational is always attractive. So there's the difference between electric and gravitational forces. So here is the force equation written out with absolute values for both charges, because remember I told you I strongly recommend anytime you're working with the electric force, calculate the magnitude separate from the direction. So the magnitude, you put absolute values so you don't have any minus signs to mess up your calculation. And here is the constant 8.9876 times 10 to the 9th Newton meters per Coulomb squared. Now notice this does have K is 1 over 4 pi epsilon 0. Epsilon 0, the permittivity of free space, is considered a fundamental constant in nature. And so K is a derived constant, derived based on pi, and that fundamental constant, the permittivity of free space. The permittivity of free space is a parameter that tells you how easily you can pass charge through a vacuum. So when we're doing problems, we will always just use K because it's shorter to write K than it is to write 1 over 4 pi epsilon 0. However, when we get to Gauss's law, we will use the epsilon 0 form. Question?
Aren't the units for K supposed to be Newton meters squared over?
Yes, they are. That's a mistake. Hopefully I said Newton meters squared per Coulomb squared. Because, yeah. Thank you. All right. So some problems. We are going to, I think after the slide, actually after 2 slides maybe, do some problems. I'm going to break you up, left side of the classroom, right side of the classroom, give you 2 different problems and have people work on them. So when we're doing problems with electric charge, the first thing that's really important is make sure you pay attention to your units. Here I have the units right. Oftentimes you'll have microcoulombs or nanocoulombs, so make sure you're real comfortable with those prefixes and you do convert the units. I myself have made this mistake plenty of times. It's not something that I, like, oh, foolish people. No, we all make these kind of mistakes. So make sure you're real careful with your units. Just shift everything to the standard SI units, to meters for distance, to kilograms for mass, no mass right here, to coulombs for charge, seconds for time as appropriate, and you won't have a problem with units. Second, when finding the force on a single charge due to 2 or more charges, just calculate each force separately. And then you just add the forces up as vectors. So if I was looking, let's suppose that everyone in this classroom has an electric charge that's going to make a measurable force. And I want to find the net force on Leslie. I'm going to take, okay, so what's the force between Leslie and Nathan? What's its direction? What's its magnitude? What's the force between Leslie and Sarah? What's the force in direction magnitude? And go for every person to get all those numbers. And then I add them as vectors to get the result. You don't worry and say, well, how is Nathan going to affect the force caused by Sarah? We call that shielding. We don't worry about that because it's all going to balance out when I add them together as vectors. Oh, there's a third one. This just says the don't worry about shielding. So here's problem number 1. Let's I've said split up by sides. Michael and Lydia, at least one of you should go over to that side of the classroom for this. And I'm going to have 6 people one side, 5 in the other. And I will assign this side of the classroom to doing this problem. And I will come back to this one because it's the more involved picture and data. For that side of the classroom, here's your problem. Make sure you write this down because I'm going to shift back to the other one. So you're asked to find the net force on this charge. And so you need to write down what each of the charges are. Make sure you get the sides. And yes, very smart, Leslie, just taking a picture. That way you're not going to miss it. Make sure you get the lengths of each side. And notice that it has X and Y defined so you won't mess that up. So I'm going to... Excuse me, what was it?
One more time to record that.
I'm sure. And so I will come back to yours after they have it all carefully recorded.
Yeah, I didn't have to use that.
Okay. DJ's got it on his clip or on his chalkboard, anybody whiteboard. So you guys can look at DJ's if you don't have it. Here's your problem. Now notice it tells you the mass of the balls. Is that important to the problem?
No.
It actually is, because if I told you before, you ignore it unless there's a reason not to. And in this case, if there was no gravitational force, they would just go like this. So the fact that they're not like this means you have to account for the gravitational force. Right, so that's an interpretive thing that you have to get kind of comfortable with. Because normally the answer would have been what you said, right?
So we know these things are we have or is that have to do with math where but we'll probably argue
But then you're thinking
oh yeah, it's electronic. Not that interpret any different values. Okay, so we just need to solve for say that there. But 113.
I think it can reverse so we're just using the force.
Get your solution.
Like from
The force came,
there.
Newton's third law. Equal opposite forces. So you're going to have the same force.
Yes. It says the 6,
And then you
negative
can
6.
go another step and look at the equation itself. It's Q1 times Q2. So all that you really can calculate here is what the product of Q1 times Q2 is, not how big each one is. That's why the last one says, assuming the charges are equal.
Right. But how do we know if they're not?
Because you
Is that
don't.
what B is at?
That's what he's asking.
So
You
we
don't
just
have a
say
way
we
of determining. The force equation is just the product of the two charges. And there's lots of different combinations of the same product.
I think it's this one and this one. Figure this one, these two, this one and this one. And then add them together. So I'm going to say it correctly.
It's the absolute value, right?
Yes.
Oh, shoot. That's. Yeah.
That's nice.
The one that happened, I didn't calculate that one, I just. So we got about 6. Yeah. 6 equals 6.
For part C, it says assume charge.
Great.
I just. Part of saying if Q1 equals Q2.
So, but the one.
Well, you know, if Q is equal to nothing.
So,
Is that an angle of 53 degrees?
Yes. Because it just goes to just
So,
Q squared.
reading exactly how we're talking. You can't just add the same direction.
Yeah. Once again, that's why you can't do this class without having first semester.
what did you get for that?
To give you guys on this side of the classroom just a hint to make it quicker, split the problem in half vertically. You only have to solve for one ball. Right, if I need second one, it's just one ball.
Yes.
Okay, then what did you get for this?
Yeah, what's that? What course is that? What course is that? The one going here. Oh, yeah.
This one here.
Yeah, this is. What's that?
So we have,
Oh, yes. Yeah. Something like that.
Okay, then we can figure out what the components are. If we have that.
what did you think?
That angle. I just took.
Oh, you just found
opposite
it.
hypotenuse, and then you sign.
Congress.
So the hypotenuse to this person radius is 0.9. You just get this back.
So what?
And that's one.
You don't know.
And then what was the force for,
The other
It's
way,
gonna-
the one that's,
No, the weight is on G.
the one that's
The
the
tension straight out the side.
0.67.
See, it's K. I'll give you guys one more hint here. Draw your free body diagram for the one ball, and then apply the second law graphically.
Yeah, about that. 6 phases will.
Geometrically, or how you say it.
So, which force are we?
So I got 1.248. And the one I just turned to something. That's the Y component of this term. And then I just added it to the other Y component that we have.
Oh, shit.
So that's the Y, and that's the X. That's acting on this.
What is your?
That number, that is the Y component of this. So I just isolated the forces going in X and Y. So in the Y direction, there's a net force of 1.248. And then in the X direction.
So you guys done this?
Because I know the angle, so I just use, and I know it's the right triangle, so I just use some force. Cosine of 53 times that. And the sine of 53 times that. The sides, the length of the sides.
force of tension.
Can you do the force of tension is not important to your solution.
It's like if you had this
If you
one,
do it graphically,
I
it's like
just found
it's
this,
Yes.
and
force tension is not important.
Oh,
You can calculate it, but it's not important for your
no.
solution.
because we use equations.
The way you're doing it, which is a perfectly valid way, it's something you
Yeah, I'm
have to
thinking
solve
we add
one
these.
side and then substitute the other two.
Yeah, if we add these two, that's that. And then we subtract that.
So question.
I don't know if he just wants one number. So these, the one that yeah.
It's what?
What's
no, you need to brought that in. It should be force tension.
Yeah.
So is it right? For the forces? That
Okay, we have 10 minutes left, and this is the time when I'm gonna call you back, so I have time to solve both of them before class ends. So, you guys wanna turn around, I'll solve both problems now. I think everybody's thought things a lot, and either you're frustrated, not sure where to go, or you're sure where to go and have gotten somewhere. So I'm gonna do this one first, just because it's the one that, well, one of them's easier, one of them's more straightforward. This is the one that's more straightforward. Not easier, but more straightforward. So using what we have already talked about, I need to calculate the magnitude of each force and the direction of each force. So first I'm going to look at the directions. These are opposite charges. Opposite charges attract. And I'm just going to call this Q2 and Q3 to make my life easy. This Q1. So this is force of 2 on 1 is pointing straight down. These are opposite, 1 and 3. So that's going to give me the force there is like this. Force of 3 on 1. Then I'm going to calculate the magnitudes. So the magnitude of force 2 on 1 is equal to K, Q2, Q1. I'll put absolute values here just to be clear. Over R21 squared is K times 0.60 times 10 to the minus 6 coulombs times 0.80 times 10 to the minus 6 coulombs all over 0.080 meters quantity squared. And can you guys give me a number for that? 0.674 newtons. Okay. Then force 3 on 1 is equal to K, magnitude of charge 3, magnitude of charge 1 over R31 squared is equal to K times 1.0 times 10 to the minus 6 coulombs, 0.80 times 10 to the minus 6 coulombs over, and I have to use the Pythagorean theorem to get what this distance is. So R31 squared is equal to 8 centimeters squared plus, oh wait, you have the 10 centimeters there. I don't, I just assumed 0.100 meters quantity squared. And what do we get for that magnitude? It's, say it again.
0.71.
Okay, 0.719 newtons. Now I have to add these to get a resultant. So, and I know I'm pretty sure I heard DJ talking about this. I need to break this force up into its X and Y components. And so I'm going to have force 3-1 in the X direction. It's going in the negative X direction, so I'm going to throw my minus sign out there right at the beginning. And then I need to break it into components. Well, if I look at this, I know that this side here had 8 centimeters. I'm just going to put 8. This side here had 10 centimeters. And if anyone is familiar with geometry, you actually know that the other side is going to be 6. And so if I consider this angle here theta, the X component is the opposite side, so it'd be minus F31 sine of theta. And sine, of course, is opposite over hypotenuse. So that would be sine of theta would be the opposite side 6 divided by the adjacent side 10. Whoops. I don't know what my hand hit, but so times 6 over 10. And so what do we get with 0.6 times minus 0.719, excuse me. What do we get for that? 81? 81?
Negative 0.43.
0.430?
1.
And then F31Y, the Y component is going vertically, so that's going to be positive. F31 cosine theta, which is going to be 0.719 newtons times 8 over 10. So what does that give us?
0.575.
And of course, it goes without saying, yet when you're doing a solution, you have to write the things that go without saying. Force 2-1 in the x direction is 0, right? And force 2-1 in the y direction is equal to minus 0.674 newtons, because my direction arrow was straight down. So now I just have to finish up by adding these together. So I'm going to have force x equals, and I take the two x values, minus 0.431 newtons plus 0.
Wait, why are you doing the 6 over 2 and 8 over 10?
6 over 10 and 8 over 10, because sine theta is opposite, which was 6, divided by hypotenuse, which is 10. Cosine was adjacent, 8 over 10. So I have my fx, my fy is equal to 0.575 newtons minus 0.674 newtons. And so that one we have to calculate minus 0.009 newtons. I should have put these in a different color, but I did not. And so then my force magnitude,
You put one too many zeros on that. It should be 0.09.
0.09,
Yeah.
575 and 674.
Should be a negative
Okay,
0.09 then.
I'm going to take your word for it. Yeah, you're right. It's going to be actually 9. Is it 9.9?
Yeah.
So square root of 0.431 newtons squared plus 0.099 newtons squared. And that'll give us the net force. And then if I wanted to get my angle, which I generally should, I would just use tangent. I'm going to stop here because, of course, I only have 2 minutes left. We've gone through what's necessary to solve it. If we look at this one, as I told them, just look at one of these, do Newton's second law based on your free body diagram graphically. So Newton's second law, sum of the force vectors equals mass times acceleration. Well, in this case, they're in equilibrium, so that's equal to 0. So I have my three forces drawn already. If I show the graphical addition of those, I will have this is my triangle, where this is the force of tension, this is the force of gravity, this is the force E. One of the things that is a little off in the way I drew it, right? You have more than one way you can draw it, is where my angle is. I'm going to redraw the triangle so my angle is easier for me to identify. I mean, this triangle is correct and would work, but it's easier to identify if I go like this. Now it's easy to identify that that's theta. And given that that's theta, I can instantly write an equation that relates the force of gravity to the force electric, the Coulombic force, because those are the opposite and adjacent. So I'm going to have tangent of theta is equal to the opposite side, force E, over the adjacent side, force G. Well, force E is Q squared, because it tells us, assuming that the charges are equal, divided by the separation R squared, all over the force of gravity, mg. So now I just need to solve this for Q. So Q is going to be the square root of mg r squared tangent theta over k. Yep, over k. There is one thing left that I need to do, and that is determine what r is. R is done geometrically. Since you know that this here is L, if that's theta, then this side here, which is r over 2, is going to have sine of theta is equal to r over 2 divided by L. Therefore, r is equal to 2L sine theta. And so I put that in, and I have my calculation for Q. This one here is actually easier to do, right? It was less work, but it was trickier. I didn't answer the first two questions. I should have. Are the signs of the charges same or opposite? What'd you guys all answer? Same, because opposites would attract. We need them to repel, so they need to be same charge. Are the magnitudes necessarily the same? No. All you can get from the force equation is the product of Q1 times Q2. It doesn't tell you how much Q1 is or Q2 is. The forces are going to be equal and opposite no matter how you cut it. All right, we're out of time. Have a great hump day. I'll see you on Friday.